Hey all, welcome to AI Daily. Let's get you up to speed on what's happening in AI today. First up, a truly fascinating development from DeepSeek, who are making waves with their new Manifold Constrained Hyperconnections, or mHC. This isn't just a minor tweak. Industry experts are calling mHC a technical center of gravity, fundamentally changing how we think about residual path design in large language models. For too long, the residual path has been somewhat overlooked, but DeepSeek is turning it into a first-class scaling lever. It's a significant shift from the classic ResNet-like assumptions, potentially redefining how LLMs are built from the ground up. Now, let's dive a bit deeper into the sheer ingenuity behind mHC. The core idea generalizes residual streams to multiple paths with learned mixing matrices. The challenge? Instability, where these matrices can explode or vanish. DeepSeek's brilliant fix involves constraining the key mixing matrix to the Birkhoff polytope, essentially ensuring rows and columns sum to 1. This clever mathematical constraint, implemented with an efficient Sinkhorn-like projection, is what keeps gradients bounded and prevents those catastrophic blowups. What a development for stability in deep networks. Moving on to the practical impact, DeepSeek isn't just delivering theoretical elegance, they're showing real-world performance. We're hearing about a reported training overhead of only about 6.7% when using 4 streams, all while dramatically improving gradient stability. For instance, the maximum backward gain is kept to a manageable 1.6, a stark contrast to the thousands you might see with a naive hyperconnections approach. This means developers can push the boundaries of LLM architecture without fear of training collapses, which is huge for scalability. But here's where it gets even more compelling. This isn't just a research paper. A significant part of the story is DeepSeek's incredible systems and infrastructure work. We're talking about a real math plus kernel team, coupling here, which is explicitly called out as frontier lab behavior. They've re-engineered kernels, optimized memory usage, and refined pipeline parallelism with fused kernels and mixed precision details. Even scheduling kernels on dedicated high-priority streams to avoid blocking, these are the subtle but critical details that make a research idea production-ready. Pay attention to this synergy. It's a blueprint for future AI innovation. Finally, let's consider the broader implications across the industry. Experts like or Taxistex are framing mHC as a basic design motif, potentially making traditional LLM assumptions less fixed. Others, like at Grigorev, are connecting mHC to wider architectural generalization trends, suggesting that if the residual stream itself becomes wider and more expressive, then perhaps MLP expansion factors could become partly redundant. This is fascinating, as it hints at a future where LLM architectures are far more flexible and efficient than we ever thought possible. And that's a wrap on today's AI headlines. Until next time,